Good afternoon, everybody. So welcome to Desal2025. It's Tampa Bay, clear water. So today is a very beautiful weather. There's a lot of nice people and beaches. Also, I'm sure that a lot of people from Australia, Europe, as well as Asia, so still trying to adjust to your jet lag. So please feel free. This is informal presentation, so no grading, so that we can have a little bit more relaxed workshop. So my name is Ho Kyung-Shan. I'm from the University of Technology, Sydney. Also, I'm trying to organize this Brine workshop together with our distinguished speakers, and we will introduce one by one. So thank you for coming today, and we will have a wonderful Q&A session, discussion, also what's going on in our desalination for the future. Also, Chelling will talk about produced water for critical mineral and water recovery. So you know that every day we have around 100 million cubic meter of desalinated water is produced. So if we can contribute some of the brine, it's like 3.5% or 4.5% from Middle East country. So we could recover a lot of salt, almost 3.5 million cubic meter per day. So there are many resources, critical mineral, we can try to recover, to have some strategic resources. And that's the reason why today we want to have a brine mining workshop to look at the opportunity. Also, we can hear about what's going on in different countries. Also, we have a lot of pilot scale going on. Also, full scale, what's the market opportunity. Also, I'd like to thank you for our audience, Professor Miriam Balaban. She's our mother of the desalination, created the desalination water treatment, and she's here today to contribute this workshop. Thank you for coming, Miriam. Thank you very much. You know that she's almost 92 years old. Right? But still, she's very hungry to travel around to learn about the desalination, how to promoted our community. So hopefully we will continue to work with William. Also, Professor Manny Alomole, so he is here to also discuss about our brine resource recovery, and then he is also very much important discussion for this important topic. Also, thank you for Amy Childress, our co-chairman. So she's organizing this workshop, also Desal2025, together with other co-chairs and SBL. So we have Janet and Joe, Tobias, they are working very hard at the behind the scene. Also, thank you everybody. And then we can start from now onwards. So what's the slide today? So we want to start with a brief introduction of our distinguished speakers from Nikolai Pachkov. Please, you can introduce yourself briefly.
Thank you. My name is Nikolai Buchkov. I'm the Executive Director of the Water Innovation Center of NEOM in Saudi Arabia. Saudi Arabia has been on the forefront of developing new membrane technologies for brine mining. And the interest in Saudi Arabia is mainly focused on the fact that the environment that we face, especially on Red Sea, is beautiful and pristine, and they'd like to keep it that way and try to combine protecting the environment with providing sources for additional revenue. So I've been in this business for over 40 years, and specifically in brine mining for about 7-8 years now. The industry is evolving very quickly. There are new technologies, new materials coming. Some of them are already available in the market, some of them are in the pipeline, and that's what I'll be presenting.
Thank you, Nikolai. So next, the Chilling, can you please briefly introduce yourself?
Good afternoon, everyone. It's a great pleasure to be here, participating in this conference and workshop, and also be co-chairing this conference with Amy. For this workshop, I thought I would introduce something that is very a big regional issue for the state of Texas, which is oil and gas produced water, because we are the biggest oil and gas producing region in the U.S., and then the produced water coming from the oil and gas production is increasingly become a very, very challenging problem, not just from the point of view of disposal, but also it's competing with other water users in the region for the freshwater sources. And so I'm looking forward to a productive discussion with you all.
Thank you, Chilling. Professor Sang.
Good afternoon. My name is Sang Lee, and I'm a professor at Kookmin University in Korea. And I've been working on membrane technology and desalination for the last more than 30 years. And I have been recently appointed as a PI for a project named Promise, which focuses on digital desalination and brine mining. So this is one of the reasons why I'm here. And other than that, I have been also working on emerging desalination technologies such as membrane desalination for osmosis, pressure retarded osmosis. So I'm going to also talk about that in another presentation on Wednesday. Anyway, I'm very honored to be here, and on today's presentation, I'll focus on how we can combine this AI with this brine mining. Thank you very much.
Thank you, Professor Sang Lee. So we have a very much different background from the industry or academia. Also we have different topics, AI. So what's happening for the desalination, AI. So Professor Sang Lee, he will introduce what's the future of AI, how we can incorporate this artificial intelligence. So that's the interesting talk he will present. Also, we have Nikolai. He has a very strong industry background to make this brine resource recovery from the Saudi NEOM City and Anwar project. Now he's working in Qatar. So he just moved, and he's also planning to have more opportunity for brine resource recovery. So we will hear about his pilot demonstration in Neom City and Chile, produced water. So nowadays a lot of produced water, so very valuable critical minerals, how we can produce from the oil and gas produced water. So we can have a very much different background and discuss about what kind of the resource recovery, AI, future of the desalination, so that we will have a very good interaction of this project. In fact, when I prepared this brine resource recovery, I received only 30 registration. It looks like we have 60, 70 people here. So I cannot really make this kind of ice-breaking time. So initially we designed for the introduce to yourself, so what kind of the resource recovery you are contributing and AI, but I will skip this one and go for our program. So I will briefly introduce what's going on for the desalination, basic background, and then Nikolai will talk about the global brine, the valorization, landscape, also chilling, the recovery of the water and critical minerals from oil and gas produced water. Sangoli, specifically, he will talk about AI with the brine resource recovery, even the general operation of the seawater desalination. And we have a panel discussion and interactive Q&A session, and think about next step, so how we can go for value of the time of these 3 hours, and then what could be the next step we can hear from you as well as our panel members. So that's all about today's program, so we can have a more friendly way of discussion. So don't be too aggressive. So just relax. Still, some people are struggling for the jet lag. So please understand if they're asking very stupid question. There is no stupid question, but still they are not really good condition. We fully understand. So just understand each other. Also, 5:15. So we have a first plenary speaker from the WDR, World Desalination Report, Christopher Gessen. So he will talk about the future of desalination, which is very much aligned with our brine resource recovery workshop. So that's today's program. So let's start. General information of resource recovery from seawater for a circular economy. So we are here. So beautiful beach, white sand beach, also Tampa Bay. So we have also desalination plant in this place. So near airport, to the south, so there is 25,000 cubic meter per day desalination plant. So this contributes around 10% of our Tampa city. So they are mixed together with the surface water. Unfortunately, it's not mixed to the clear water in this area, mainly the main city near airport. So this desalination is located here every place. And then we are very much fortunate to have this opportunity to talk about beautiful beach, seawater, and desalination. And seawater is a reliable water and food, mineral, and energy resource. So we have a lot of seafood, and we have water. Also, you can see the salt, almost 55% chloride, sodium, followed by sulfate. So there are many concentrations we have. Also calcium, potassium, magnesium. They are also major component in seawater. Also we have monovalent iron, lithium, and rubidium, also valuable rare earth elements contained in seawater. So how we can recover? So how this is cost effective to recover this kind of valuable salt. So that's what we want to have a discussion. And this is the information for desalination. Already I mentioned about every day 100 million cubic meter per day desalinate water is produced. So if we recover most of salt, 3.5 cubic meter per day of the salt we can produce. So you can see the desalination is keep increasing, reverse osmosis, MSF and MED. So if we have more salt recovery, so there are many benefits we can try to engage to make a more value for seawater desalination. Not only produce but also salt we can generate from the seawater desalination. So this is the typical seawater desalination plant. So most of people currently utilize the Brine, but we have annual NEO project. So there is a different way of process as a pretreatment, nanofiltration. So this is the changing of the whole process. It's not like a pretreatment, RO, and post-treatment. So we have nanofiltration as a pretreatment to separate the monovalent, divalent ion. In this case, the process is very much different from the typical reverse osmosis. So the Nikolai will introduce what's his experience, nanofiltration. So what kind of nanofiltration, level of monovalent, divalent, how we can maximize the overall process design. And this is the SWRO, so most widely used desalination currently. So we have first generation reverse osmosis membrane. Still a lot of people are trying to improve reverse osmosis. So this is just a never-ending innovation, but 1960, they have a CTA membrane, reverse osmosis. Since then, we have benefit a lot for reverse osmosis. And we have also second generation of the breakthrough for energy recovery. So pressure exchanger saved a lot of the energy cost from 10 kilowatt hour per cubic meter to 4 kilowatt hour cubic meters. For very recently, the Canary desalination plant, they announced that they developed world record-breaking the seawater desalination energy consumption, less than 3 kilowatt hour per cubic meter. So still, a lot of people, less than 2 kilowatt hour per cubic meter for energy consumption for Canary desalination, right? Yes. Wow, that's another. Natural. Yes. Depending on the thermodynamics, it's natural. You should have done this way, but we are still behind. But less than 2 kilowatt hour per cubic meter. Yeah.
But we don't know if they use, if they account everything or just part. Anyway.
But anyway, it was last week. So on the desalination news, they mentioned about
Guinness record. Guinness.
Guinness. Yeah, right, Guinness.
It's like
Guinness record breaking for less than 2 kilowatt hours. So we have to figure it out what kind of the energy calculation they made, so that we have already very much big progress of the energy consumption. Not only 4 kilowatt hour per cubic meter due to pressure exchanger. So now it's less than 2 kilowatt hour per cubic meter of the seawater desalination is coming very soon, which means desalination is very cost effective compared to wastewater recycling, even drinking water. So this seawater desalination becoming more cost effective. So if we can add more AI and the resource valorization, so we will have a further value of the seawater desalination. So that's the today agenda: brine mining and AI and steel. low energy desalination, less than 2 kilowatt hour is possible, so maybe less than 1 kilowatt hour per cubic meter, so we can continue to try to make this kind of seawater desalination contribution. So I look at what's the papers at this stage. So I look at only SBR, brine resource recovery. So a lot of people, they try to recover from seawater desalination. So this year, only like almost 80 papers we have published. For last 7 years, so we have significantly increased the overall number of our desalinated paper for brine resource recovery. I'm sure that this will just the beginning, and we can have a more exponential growth of the brine resource recovery publication, especially people focus on more about lithium because of battery and then electric vehicles. The battery is becoming more important value of our energy source. So lithium is number one, and then calcium, magnesium, followed by also sodium chloride. So that's the way of the people try to look at how they can recover the resource from the seawater desalination. So this is the main three projects for the brine resource recovery. C4 value from Europe, so they try to recover 10 major elements: magnesium, calcium, rubidium, lithium, and they utilize the different technology, and they have, you can see the multivalent ion and monovalent ion, so how they can try to separate using nanofiltration, and then look at the different precipitate, magnesium hydroxide. Also, they have a different technology to have a monovalent ion recovery and then the multivalent ion. So they have used absorbent, also electrochemical process, and some of the dialysis, the bipolar membrane, to produce the different selection of monovalent ion and divalent ion. So they have done this kind of study for last almost 10 years, and then try to make a more bigger scale. Also, this is the NOI. The Nikolai will explain more detail. So they already have demonstrated the 1,000 cubic meter per day of pilot scale using this kind of scope. So you can see the nanofiltration and the seawater reverse osmosis, and how they can separate multivalent, divalent ion, and calcium, magnesium for the divalent ion. And they have also calcium, potassium chloride, lithium chloride, and cesium, and sodium chloride, as well as the rubidium. They have recovered for this rubidium compound from the seawater brine using some of the Prussian blue absorbent. So they have also absorbent technology, electrochemical nanofiltration. Then this has been operated for last couple of years to make this happen for resource recovery from seawater brine. And very recently from this year, so Professor Sang-Ho Lee, he's leading the PROMISE project. So this is supported by the Korean government, and they want to have AI technology together with the resource recovery. So utilizing the CO2 to make calcium carbonate, magnesium carbonate, and then make some construction material to utilize this construction material production. Also, they are trying to recover sodium chloride and bromine and also monovalent ion. So 13 different elements: lithium, potassium, rubidium, strontium, and vanadium. So 13 different monovalent ion and divalent ion is trying to recover. So this project just launched a couple of months ago, and they will continue this project for next 5 years. So they want to have AI and this resource recovery together to develop the smart desalination plant. So this project is more about different generation. So this project mentioned about they like to challenge the first generation. So Professor Sang-Ho Lee mentioned about first generation technology, second generation, and third generation, and AI and resource recovery will be the fourth generation of the desalination. So his talk will be mentioned about how this fourth generation of desalination will happen for the future. And this is the Saudi Arabia, they have contributed for the resource recovery. So most promising potential revenue from seawater brine would be sodium hydroxide using the chloroalkali industry method. So this is the sodium chloride electrodialysis, and then produce their sodium hydroxide, also hypochlorite. That's why they can utilize the very pure acidic and alkalic concentration. So we will have more opportunity to look at this first step, potential revenue. Also, second one is the magnesium, and third one is the HCl sodium chloride, followed by rubidium chloride. So that's the way we believe the potential revenue will happen for this brine resource recovery. And then we will have a more discussion today whether this is the possible or how long it takes to reach to this level. So this is the general information, what would happen so far, and then in the future, what kind of the desalination, how we can achieve cost-effective and the value-added desalination with the smart way of the AI-driven desalination plan. And we will go for next detail of the information for real plant operation from the Nikolai. So he will talk about what's his experience from the pilot scale of resource recovery. Please join me welcoming his talk.
My presentation will be very much giving an overview of where we are with practical implementation of brine mining. It is happening slowly, but there are a number of projects that you may have heard of, and I'll mention also a few projects that are in the works, and what is new and different in those projects from what you may know or have seen in other presentations. What is brine valorization? That's basically harvesting of valuable minerals from the brine. Often people refer to it as zero liquid discharge, but those are two different things. Zero liquid discharge is a side effect of brine valorization, and when we start looking at it in NEOM, trying to get to zero liquid discharge as a prime goal, we found that that's not necessarily very cost effective because of the looking at it, and as many do, of removing brine as a waste product, as a mixed brine, which has no commercial value. That's why we have to reconsider and look into other options where we could actually valorize minerals that can be produced and sold at competitive pricing compared to what we have on the markets today. Next is I'd like to talk about, which is part of the brine valorization, is producing green chemicals from the brine. At this point, in NEOM and other locations, there is a significant amount of work trying to figure out how can we produce every single chemical we use in full-scale desalination plants from brine. And now we know, and we've been doing that for a while, and I'll explain briefly what is it that we do to be able to get basically to what we would refer as circular economy, where we don't have to buy any chemicals anymore. We could actually extract everything we need from the brine itself. That is a significant step forward, and it will continue developing as time passes. And then another point that I would like to discuss is the use of brine for various non-chemical industry products, like for example producing concrete. That is becoming very popular, and in Saudi Arabia it's now widely used for restoration of corals in the Red Sea. It is very surprising to see, but logical, that if you put one piece of concrete that is made out of typical concrete constituents, and one that is actually made with brine that contains a lot of calcium and magnesium, the shellfish and the coral does know which one is which, and they prefer and populates much faster the one made from brine. So that is an interesting fact and observation which caused brine products to be of significant benefit. We in NEOM have sold over $10 million worth of actually this type of brine restoration process. So it is very much possible. As you've seen this figure before, in desalinated water, 86% of the salts are sodium chloride. Sodium chloride is considered of low value if it is of low purity. However, we have developed technologies in the industry today that allow us to get to purities of 99.6%. Purity that we get from a common solar ponds are about 96%. That mineral is not necessarily very suitable or valuable for the chlor-alkali and other chemical industries. It's much, much more valuable to go to 99.6% purity. Just to give you an example, the cost of 96% purity, that's brine obtained through solar evaporation, it's about $25 a ton. 99.6% purity of the same sodium chloride is $75 a ton. In some countries, like Indonesia, it's $120 a ton. So actually producing high purity products significantly improves the possibility for us to have a revenue. Besides the sodium chloride, the next in line, as to say, as far as substance, is magnesium, potassium, and calcium. Those are the key minerals that get us to approximately from 86% to about 92-94% of all minerals. The rest of it is small micro minerals, which, however, could have very, very high value for the future of the industry. And as was mentioned by Dr. Sean, we actually been working with them on developing rubidium selective membranes and rubidium selective resins, and why is rubidium so interesting for us is because what you don't know yet, but hopefully you'll hear soon, is the next fuel for production of energy is actually rubidium chloride. There are reactors that have been developed. They're not yet publicly available, but they will become soon, which run on rubidium chloride, and they're extremely efficient. Produce directly electricity. There is no nuclear process involved. So rubidium may become the future of power. This graph shows a very important fact, and that is if we compare what we have today as terrestrial sources of minerals that we normally would achieve by having terrestrial mines, surface mines, and we compare the same minerals to what's in seawater, you will see many orders of magnitude higher amounts of all key minerals in seawater than the same minerals in known and available terrestrial mines. What that tells us is that ocean could become and will become the next main source of minerals worldwide. Because of the terrestrial mining involves significant environmental pollution, and also it becomes more and more complex. The mines that we're using are more difficult to get to. The price of production of the same minerals from brine is becoming very, very competitive. This figure shows basically that not every mineral today, with the existing technologies we know and have, would be cost effective to compete against what is available in the market through terrestrial mining. The line, all the black spots are indicating minerals that we don't have yet technologies to develop. So for you as researchers and scientists, it's a great opportunity to develop those technologies that are below the dotted line, the black dots. They indicate how many valuable minerals we have, which we need to get to the point where we could produce them competitively. The minerals above the line are all minerals that we do have technologies for today. They do exist, and some of them are used in practical applications to actually mine them at more competitive prices than what we would do from terrestrial mining. And as you would notice, sodium chloride, potassium, magnesium, and calcium are on the top of those. You would see also rubidium in that. We can also mine uranium, iodine, bromate. So those are valuable minerals that can be, at this time, extracted at lower prices. Where do we start? It makes sense to start with sodium chloride because 86% of seawater salt is sodium chloride on one end. On the other end, it's a fairly expensive mineral and there is a huge demand for it. Majority of that demand is in the Middle East, but also in the US, China. And what is it that sodium chloride is used for, besides the normal uses that we know? It's used mainly in the chlor-alkali industry, and in the Middle East it's used because it is an attractive way of making liquid PVC. Liquid PVC is made of two substances, sodium chloride and oil. If you have both, you certainly can produce liquid PVC. Then liquid PVC, by adding various additives to it, can be converted into any plastic that we know and use today. So that really opens up a big market and industry. And what is interesting in this calculations is I wanted to show you 100,000 cubic meters a day desalination plant, which nowadays would be considered medium size. It used to be big size, but nowadays big size plants are 1 million cubic meters a day and more. So if we take a 100,000 cubic meters a day plant, we can produce out of it about 1 to 1.2 million tons of salts per year. If we look at the annual revenue, if we are selling that water that we produce at the plant at 60 cents per cubic meter, which is a reasonable pricing nowadays, we will be getting revenue of $22 million per year. If we look at the sodium chloride sale as extracted currently through available technologies, we could sell it for $65 to $75 per ton. So the revenue, as you notice the two numbers, the revenue from water is significantly smaller than revenue from brine. So if we can find the place to sell the brine, or portion of it, even 1/3 of it, we will be producing revenue much higher than water supply. And that is a very interesting observation because it changes the paradigm of desalination. If for those you may have not been to Indonesia to see the first large-scale project, you know what happened with the desalinated water? It goes back to the sea and it's given away because the manufacturer is interested in the salt. And when I ask him, hey, this drinking water, why are you dumping it back? I have nothing. I mean, I make $60 million out of salt and less than $1 million out of water. I'm not going to bother with water. I just give it away. That is actually a very interesting and real example of where the industry is going. The most expensive source of water could become the cheapest source of water as long as we can cost-effectively remove minerals and sell them. So if we look at this, we can see at $40 a ton of production cost, which is actually the cost of production in Indonesia is $40 a ton. That's why I picked that number. So at $40 a ton, we have profit margin of $25 million per year of selling the sodium chloride. So it shows us that the profit margin is higher than the sales of water. It allows us a mechanism by which we can actually turn desalinated water to a main water supply source. Currently, only about 1.5% to 2% of the world's water is supplied by desalination. By tapping into brine mining, we actually can dramatically increase that amount as long as we have industrial development around us. Or even when you think about third world countries or global south, they can, even if they don't have immediate use, extracting those minerals can actually make them very attractive source of rare minerals and metals. This particular graph shows if we take 1,000 cubic meters a day of seawater, how much, and you see the cost of it, how much we are extracting from the various sources. As you notice, sodium chloride, and this is based on market costs in Saudi Arabia, but also in many other countries, things like sodium hydroxide, magnesium, hydrochloric acid, those are all substances, chemicals that we could extract at very attractive pricing at present. The first large-scale plant that I mentioned was built in Indonesia in 2022. This actually presents the schematic of the facility. We have ultrafiltration for pretreatment, followed by nanofiltration to split the monovalent and bivalent ions. In this case, the client there, which is the food industry, is only interested in the monovalent, so that the bivalent basically is disposed of. So after we go through nanofiltration, seawater reverse osmosis separates the salt. At this point, the sodium chloride is the main salt in the brine. Afterwards, osmotically assisted RO is used to concentrate that salt to approximately 180 to 100,000. And then the concentrated salt is crystallized. What is interesting to underline here is this plant produces 0.2 million tons of sodium chloride per year, and crystallizer power demand is 5.3 megawatts per hour, and which is 50% of the total power demand. Why is that important? It is because it shows us one very important issue. The main cost and energy associated with brine mining is in the crystallization of the product. So if we could avoid it, avoid crystallizing it, pumping it to directly as liquid, or use alternative crystallization like membrane crystallization, we can actually make a very significant impact. As I mentioned, this project produces a brine at $40 a ton. If you use solely membrane technologies, that number goes to $18 a ton. Very competitive production cost. This basically shows the water treatment costs against various technologies. What is the important of this is the energy demand significantly increases as we try to concentrate more and more. That's why we have to start looking as an industry into a different way of concentrating and crystallizing. Concentration and crystallization are 2/3 of brine mining energy demand. This is an example of a plant that is currently being developed for the Jubail, city of Jubail in Saudi Arabia, and that's built in parallel with existing desalination plant. And that plant is 1 million cubic meters a day, and portion of the brine, a relatively small amount of it, is collected from the seawater RO system and then processed through membrane brine concentration, followed by crystallization, in this case thermal crystallizer, and then the two beneficial minerals produced are crystal salt and bromine. Why is bromine beneficial and where is it used? It is used in every well in the world that makes fuel oil. It is actually fire retardant. It is injected in the wells of every country that makes oil, and therefore has a huge market if you have that type of business around. Another facility, and that's the one in Dubai, Saudi Arabia, developed by NEOM, has a similar process to the one that you've seen, but it also focuses on, so we have ultrafiltration for pretreatment, seawater reverse osmosis, and then we ultra high pressure RO, but this one also has a slightly different component. Ultra high pressure RO, which the other facility didn't have. Ultra high pressure RO takes the brine from the conventional seawater RO system and concentrates it from about 68 to 70,000 to 120,000 TDS. And at the same time, ultra high pressure RO produces water. That allows us to increase the recovery of a conventional seawater desalination plant, which is about 43%, to all the way to 65%, and produce obviously much more water, and at the same time concentrate the brine. So starting from 120,000, the brine is then reconcentrated by osmotically assisted reverse osmosis, and then the concentrated brine, in the case of Dubai, gets split into two streams. One is actually thermal crystallizer, the other one is a membrane crystallizer. So we're running side by side the two technologies to see which one works better and what's the difference. That is very important because, as I mentioned, most of the energy in this type of facilities is energy for crystallization. So if we dramatically reduce this energy, we can dramatically reduce the cost. So when we look at this system, overall water recovery is 86%, so it's twice the 43% that we recovered. That's one advantage, we're producing more water. Second, salt recovery is 92%. All of those salts are actually of commercial value. Cost of water production is about 50 cents, and cost of sodium chloride production is about $35 per ton. This is with thermal desalination. As I mentioned, if we go with membrane crystallization, we would actually end up to $18 a ton, about a half. And that is because the energy demand for thermal crystallization is significantly higher. Just to give you a sense of kilowatt hours, the kilowatt hours per cubic meter of brine processed is approximately 75 to 80 kilowatt hours per cubic meter of processed brine, crystallized brine. In the case of membrane crystallization, that amount is 7.5. 75, 7.5. That is a dramatic decrease in energy demand. This is the plant, and it shows you in summary what are the key components of the plant. I already mentioned them. The membrane crystallizer for the facility, you could see it at the bottom corner here. This component, it is fairly small and efficient. One very important component that really will change the world of brine mining is how we look at membranes. And that is when we tried to fund a project in Qatar, the investors were asking, okay, you have all these great minerals, and they're needed today, like magnesium and calcium and others. But what happens if nobody cares about magnesium 10 years from now? We know water will be needed 10 years from now, but what if the minerals that we're interested in today are great business proposition today, but 5 or 10 years from now, they're replaced by plastics, by other metal, as it was aluminum 10 years ago? And that's a very fair question. So it's very difficult to make brine mining on a large scale financially viable because of that reason, especially if you're producing many different minerals. And the solution to that is actually to develop membranes, which include special components inside them, ionophores, which actually can be selected for the particular mineral you would like to extract. So if tomorrow we want calcium or potassium or lithium, all we need to do is go to the seawater RO system, take the existing membranes, and put those that are selected for that particular mineral. That allows us to evolve as demand changes, as also the minerals that we are extracting change. We could use exactly the same seawater RO system and extract various minerals. We will have more opportunity for questions, so I don't have as much detail to discuss, but when you look at the plan of the future, you imagine multiple RO trains, some of them with membranes selected for lithium, others selected for potassium, others selected for magnesium. And I point out magnesium and magnesium selection because the membrane crystallizer that we use actually runs on draw solution of magnesium chloride. And we actually make our own magnesium chloride by directly extracting it from seawater. That allows us, when you bring the pH down of the water to about 4, all the magnesium switches to magnesium chloride, then through the selective membranes we remove it and recover it, and we use it as a draw solution for the membrane crystallizers. That actually closes the loop of cost-effective membrane crystallization, which otherwise usually the draw solution is the big challenge of how do you make that draw solution cost-effectively. In our case, we're making it of seawater. We're not buying it from outside. This is the membrane crystallizer. You can see the tiny crystals forming on the surface. This demonstration facility is for 40 kilograms per day. The total demand is 7.5 kilowatt hours, of which about 7 kilowatt hours goes for production and crystallization, and 5 goes for recovery of the brine solution. What's interesting about magnesium and why we picked it is if you look at temperature versus concentration, we only need few degrees change in temperature to double the concentration of magnesium chloride, and we're doing that through a cooling tower. So it's very easy and very low energy to concentrate magnesium chloride. That's why we picked it. This is the membrane crystallizer, 7 kilowatt hours for the crystallizer, 0.5 for the cooling tower, which is used to recover and reuse the draw solution. So compared to 80 to 85 kilowatt hours, that certainly breaks the energy barrier for desalination. I wanted to just say a few things about mineral products, and that is that the purity is very important for any of the products that we make, commercial products. The main problems that minerals create are magnesium, calcium, and potassium. They would have to be removed for the chlor-alkali process to be cost effective. And how do we do that? At this point, there are ways through dialysis and others, but now we're actually doing that through selective membranes. And if you ask me questions, I'll be able to answer in detail, but at this point we don't have the time. We also, as I mentioned, are generating plant chemicals from brine minerals, coagulant from magnesium hydroxide. Magnesium hydroxide is an excellent coagulant compared to ferric chloride. Anti-scalant from balancing of calcium and magnesium. If you ask me, I'll explain later because it's a little bit more complicated. Draw solution, magnesium chloride from seawater, as I mentioned that. Biselective seawater membranes, and calcium carbonate from the CO2 sequestration using nanobubbles, and that's where's Hamid, Texas A&M. He was here earlier. Yeah, so that idea came from him, and it's an excellent idea because it minimizes the cost of and efficiency of use of CO2. This is printing, 3D printing with brine, and as you can see, those are the shapes I mentioned that we use for coral reef habitat restoration. This already have been deployed. And then what is next? That's the main issue that we would like to understand and work towards, because you're the scientists that have to make it happen. First is multifunctional membranes. Seawater membranes for the last 50 years make only one thing, water. Now with brine mining, we are making membranes that can make more than one thing. They make still water, but also they would make a specific mineral. Currently, we've developed membranes for potassium chloride, lithium chloride, rubidium chloride, and magnesium chloride. That is possible by using different ionophores for every one of those substances. The same principle of production. NF membranes with magnesium rejection of 98%. We actually achieved that. Currently, we are achieving, using a company called Active Membranes, which you may have heard, we're pushing the envelope of 96% recovery in the NF system. Currently, recovery is at 75% with conventional membranes. So that's new. Brine membrane crystallization, forward osmosis to crystallize the brine to the level of commercial product. High pressure brine concentration, that is happening. There are new products that were just recently introduced. Increase in desalinated recovery from 86 to 96%. Thermally resistant brine membranes. One thing that you will see in the Middle East is very high temperatures of seawater. And as we pump and pump and pump to concentrate brine and crystallize it, we would end up at a point where we will hit the 40 degrees Celsius maximum, which will compact the membranes. So companies like Hypernautics, FTS, and now Dow are currently working on thermally resistant membranes where they operate up to 45 degrees Celsius and guarantee performance without compaction, or with typical minimal compaction. Post-treatment of seawater RO, post-seawater RO NF membranes. One thing that you also will see in practice is every time you go and talk to real people about real projects, they say, don't touch my seawater RO system. You can take my brine, but don't put NF on the front of my seawater RO. So that basically caused the industry to develop a completely new set of nanofiltration membranes that are operating for splitting minerals on the back end, taking the brine, mixed brine as it comes from the seawater RO systems, and splitting it. The latest elements that we're developing currently actually also selectively remove sodium and potassium out of the product. So we create extremely high purity sodium chloride. The other thing is generating all desalination plant chemicals from brine. This is what we strive for, and it's possible. That by itself is certainly worthwhile for you as scientists to consider. There are opportunities to develop new technologies in for various chemicals, but it's all doable. Everything can be produced from brine, and that is a major breakthrough in terms of circularity and desalination. With that, I guess we have a 2-minute question and answer. And then at the end, we will have discussion at the end of the workshop for all questions you may have.
Just one burning question. Anybody just come to the mic, and then you can ask now one question. Otherwise, we can, please.
Quick one, I don't know.
Yes, quick one. And then we will have a more discussion after three speakers' talks.
Yes, thank you for the presentation. Professor Desal2025 from Kuwait University. I started working on the brine you call it here brine recovery, we call it the brine management. I started with MIT for 7 years. I was the leader of the project, 5.5 million. The focus here about the power and the cost effective. We looked at both, also environmental impact. To us, environmental impact is very important, sustainability, because of the fauna and flora, the marine species, and also the brine is heavier than the ambient seawater and settles and causes
Unless mixed.
stratification and stuff like that. So in our projects, and we started very early, 2013, on the brine management. We did the treatment. We used ED, electrodialysis, pressure retarded osmosis to produce green energy from brine, iron concentration polarization. We got the patent with MIT. This is a treatment, and also disposal. We dispose it in a smart way to reduce this the density of the brine, and instead of settling, we just had it on the surface and then dispersed. So I do really support the cost effective, but also the environmental impact and sustainability extremely important for us to protect the coastal line is priceless.
Yeah.
Thank you.
Thank you. Yeah, I absolutely agree with you. That's really the reason why Saudi Arabia has invested a significant amount of research and funding in research, because they have a beautiful, pristine coral reef area along the Red Sea. And as we are looking at industrial development at this point and resorts, the main concern is, okay, now we're bringing a lot of people, we will have brine, water has to be produced and brine has to be generated. And we know from my experience here in Florida, we bleached our brine, our coral, and if you'd like to go and see real beautiful coral, which we do have here as well, you have to now go about 3 to 4 miles out. You would see all the coral basically die. That's one thing we don't want to do in Saudi Arabia, and by this approach, we're combining environmental protection and at the same time beneficial reuse of brine. We call it brine valorization because we're basically turning brine into a commercial product. Thank you.
Thank you, Nikolai. Wonderful presentation. So next speaker is Professor Li. So she will talk about recovery of water and critical mineral from oil and produced water. So please join me in welcoming her presentation.
I really appreciate that first presentation that gives you a very high level, introduction on where we are and brine mining. And I'm going to talk about a specific source of brine. Seawater, mining minerals from seawater is great and has both environmental benefits as well as financial benefits. And other industrial brines a lot of times make even more financial senses because we're dealing with much higher concentration of salt, as well as an industry that can afford to actually pay more to desalinate their wastewater. So as I mentioned earlier, I'm from the biggest oil and gas producing region in the US, in Texas. Produced water from oil and gas production has been and is increasingly becoming a very urgent challenge in the region and in many other oil and gas production locations around the world. This wastewater is produced when you pump oil and natural gas above the ground. So what comes up is a mixture of water, oil, and natural gas. And once you separate the three phases, you get a water that has very high concentration of hydrocarbon, but at the same time in our region, extremely high salinity concentration. So in many places, the salt concentration can be over 200,000 milligram per liter, so many times higher than seawater. In the past, and still ongoing practice, is we take this wastewater and you dump them into deep injection wells. So those are wells that are several thousand feet in depth, drilled into the ground. And in Texas, we have a lot of these disposal wells. In the past, that has always been the disposal location of this wastewater. But in the past couple of decades, there have been more and more frequent seismic activities caused by the disposal of produced water. So in a lot of places, disposal through this approach is no longer an option. But this water needs to go somewhere, right? At the same time, the oil and gas production usually happens in highly arid areas. In Western Texas, the farmers are running out of water, and so there is competition between the oil and gas industry and other water users for the freshwater resources, because the oil and gas industry not only produce a lot of wastewater, but they also require a large amount of water to produce oil and gas. So they, especially in places where they have to do hydraulic fracturing for production. So there you have a large water demand, but at the same time you have to dispose of a very large volume of wastewater. Then recovering water from that wastewater makes a perfect sense. The challenge again is the very high salinity and the large production volume. In the Permian Basin, where a large part of the Permian Basin is in Texas, the water to oil ratio is about 5:1. So in other words, every cubic meter or every barrel, that's what the oil people say, every barrel of water produced, you will produce 5 barrels of wastewater, and that's highly saline. So if there's a cost-effective way to recover the water from that wastewater and use it for beneficial purposes locally, and then that would be of great financial benefits to the producers as well as to the local environment and local communities. Now, another very attractive reason for treating that water is that there are actually high concentration of minerals in that wastewater. There has been reported that lithium concentration as high as several hundred milligrams per liter is present in many locations in that produced water. So if we can recover water and these critical minerals, including lithium, then we're benefiting from both sources. Now, I'll talk about the recovering of fresh water from this highly saline wastewater first, right? So this is a plot we adopted, I think, from Tianjin and Venice, one of their publications that looked at the desalination technology landscape, especially in the brine concentration and zero liquid discharge space. So if you look at the brine concentration, which is where I think the oil and gas companies is most interested, because for them, they wanted to reduce the volume they have to dispose of and extract fresh water, and whether or not they whether or not they can extract minerals from it is not as important, but of course that can negate their cost of the treatment, right? So that middle zone, the brine concentration range from 70,000 to up to 200, 250,000 ppm is the concentration, TDS concentration range of interest. So in that concentration range, the most common approach is obviously thermal evaporators, and that works well, and probably the only mature commercially available technologies out there for them to consider, but very, very energy intensive. Membrane-based technologies such as ultra-high pressure reverse osmosis would have been a lot more energy efficient, but right now the commercial reverse osmosis membranes cannot really provide or stand the extremely high pressure necessary to overcome the osmotic pressure of that hypersaline wastewater. So a lot of people work in the space of thermal membrane brine concentration, that's what we call them. One of the technology is membrane distillation, but still the technology is much more energy intensive than if you would have achieved using reverse osmosis based technology. So the goal is to reduce the energy consumption of these thermal membrane brine concentration technologies, at the same time and make sure that they can even cover TDS range that's higher than what the current RO membrane technologies can. As I mentioned, a lot of people working on membrane distillation technology. It has a lot of attractive features: low temperature, low pressure operation, and it allows you to potentially use low-grade heat energy and renewable energy, for example, solar energy, and it's less prone to fouling than reverse osmosis and relatively insensitive to TDS, but it has two fairly fatal deficiencies. One is that current MD technology has very low thermal efficiency and very, very low water recovery can be achieved through this process. And the very low thermal efficiency is caused by several factors, temperature polarization being one well-known contributor. The diminishing temperature difference when you scale up the membrane module is a second very important reason, and of course thermal energy loss to the brine and the environment is a third contributor to that low thermal efficiency. If you look at this technology, through a thermodynamic point of view, this technology really cannot be a scalable technology, right? As I mentioned earlier, when you scale up the membrane, just like any heat exchanger, when you increase the membrane size, because the thermal energy input to the membrane unit is tied to the feed water flow rate. So when you increase the membrane size, you will experience diminishing average temperature driving force across the membrane module, and therefore diminishing average membrane permeate flux. At the same time, because the thermal energy input is tied to your feed water flow rate, right? So you can only heat your feed water up to 100 degrees Celsius under ambient pressure. So you're limited by how much thermal energy you can put per unit area of the membrane. So your maximum water recovery, even if we assume 100% energy efficiency, is less than 30%. So there's not a way to get around that. One approach that a lot of researchers have worked on is to decouple the thermal energy input from the feed water flow rate. So in this case, we can provide heat, not by heating the feed water, but provide the heat by heating the membrane surface. So interfacial heating or surface heated membrane distillation has attracted a lot of attention in the past decade or so. And there are several different approaches you can heat the membrane surface. You can use light with a photothermally active membrane coating surface, or you can use dual heating, so electrically conducting membrane can conduct a current through the membrane surface, and the resistive heating can create a high temperature on the membrane surface. Conduction heating and induction heating are two other approaches that have been used. And if you compare these different surface heated membrane distillation method, and you can see that the photothermal approach, and most of the time people try to use natural sunlight, can get you a very high energy efficiency. So compared to conventional MD, all of these surface heated membrane distillation processes have much higher energy efficiency. But if you try to use natural sunlight, because the very low intensity of sunlight, so on a global average, you have about 1 kilowatt per meter square of irradiated area in sunlight. So that very low light intensity results in fairly small permeate flux, even though you can get to a high energy efficiency. So the other surface heated methods has increasingly attracted more attention because you can provide much higher energy intensity and therefore achieving both. Let me get the laser. You can achieve both high flux and high energy efficiency at the same time. So if you look at this upper right region, where you can get a flux that's equivalent to what you can achieve with RO at much higher TDS, but also very high energy efficiency, more than 80% energy efficiency can be achieved if you manage the design of the membrane module properly. Now, any thermal methods is still, even with more than 80% thermal efficiency, is still going to be very energy intensive, right? Without any heat recovery and reuse of that thermal energy. So are there cheaper ways to recover the heat without using expensive heat exchangers? So one of the approaches, you can create a multi-effect membrane distillation module. In our study, we developed a multi-effect design using a spiral wound configuration that's very similar to what you see in a reverse osmosis membrane module. So the natural spiral wound structure provides multiple layers of membranes and allows you to recover the heat of condensation and use on the next layer of membrane to drive vapor evaporation again. And to overcome the limitation of the low thermal energy of natural sunlight, you can couple this technology with a parabolic solar trough concentrator. So that allows you to use concentrated sunlight on the membrane surface, and the concentrated sunlight increases the membrane permeate flux non-linearly because vapor pressure increases non-linearly with temperature. So you can drastically improve membrane permeate flux when you are using concentrating sunlight, also improving the thermal efficiency. But this means that you're going to need a very large land area to harvest enough sunlight to drive this still relatively slow process, right? So if you need high throughput, so in the case of oil and gas produced water, high throughput is really necessary because they're producing huge amount of water every day. Solar membrane distillation is means that you're going to have to build massive desalination plant to treat the flow rate necessary. So another approach is to use electricity. So the joule heating approach can allow us to provide much higher thermal energy intensity into the system. But the challenge in joule heating in treating high salinity water is that most of the conductors are metal-based, and so in a hypersaline water, electrochemical corrosion is going to immediately damage your electrically conducting membrane. So in this case, we take advantage of a two-dimensional nanomaterial hexagonal boron nitride, which forms this beautiful two-dimensional nanoscaled layer. We can grow it on a commercial stainless steel mesh. So you can see here, this is a hexagonal boron nitride coated stainless steel mesh. It looks just the same as your typical stainless steel mesh, but it's protected by the HBN nano coating. The HBN nano coating has several very unique features. One is perfectly impermeable to water or any salt ion. So this isolates your electric current from the surrounding salt solution. Secondly, it has extremely high thermal conductivity. And so any heat that's generated by the stainless steel mesh can very quickly be transferred to the surrounding brine solution very efficiently. Three, HBN is also a very strong material, has very strong mechanical properties, so it can resist scratching, scouring by particles as well. And so if you put this coating on a traditional membrane distillation membrane surface and use that as your heating element, and we also designed a spiral wound configuration where you have two pieces of membranes with the HBN coated stainless steel mesh sandwiched in between. Now where the heat can be used in both directions to drive vapor transport, and you can build a spiral wound configuration. And with that, you can actually achieve both high membrane flux as well as high thermal efficiency. So you can see here the spiral wound configuration almost doubled the energy efficiency of the flat sheet configuration using the exact same surface heating element, and it can handle TDS concentration. Here I'm going to show you on another plot. Up to 250,000 ppm of this. In this case, we tested in sodium chloride. So if you compare the throughput that can be generated by this approach with conventional reverse osmosis, right? So reverse osmosis has very high throughput because of the high permeate flux, but it's limited by the TDS concentration it can handle. The electrothermal membrane distillation can take that TDS range all the way up to 250,000, but produce membrane permeate flux that's very, very similar to what you can achieve in an RO system. And the HBN coating also has the additional advantage that because it's super smooth, it's atomically smooth, and it also has a modulated polarity in its surface chemistry, so extremely resistant to scale formation. So here we compare scale formation on four different material surfaces: traditional polished titanium, and your smooth PVDF surface, graphene, which is another atomically smooth material, and HBN. HBN by far has the lowest scale formation potential. Now, with the few minutes I have left, I wanted to talk about the critical mineral materials in these produced water sources. So if you look at the main minerals in this produced water, of course, chloride is the most abundant ion in this produced water. Then the most abundant cation is sodium. But you also have significant concentration of lithium, cobalt, nickel, magnesium, and manganese. And if you look at their concentration together with the total amount, what we think make most sense are actually lithium and magnesium. So in 2017 alone, the lithium and magnesium content in this produced water in the US can meet 300% and 1800% of the US annual demand for these two elements. So if we can recover these elements cost effectively, then we can solve at least the dependency of US's dependency on lithium supply chain. So currently lithium is mined from either hard rock or brine sources. And the brine mining of lithium is very slow and not very environmentally friendly because it involves a lot of chemical precipitation and use of huge evaporation pond. So for environmental protection purposes, we wanted to avoid using this conventional lithium mining method, and so instead use direct lithium extraction, where you don't have to, well, you can skip the evaporation ponds. Now, a lot of the direct lithium extraction methods utilizes lithium selective adsorbent. So after pretreatment to remove suspended solids and some scaling materials, and you would remove then calcium and magnesium, which interferes significantly with the lithium absorption on the selective media. Once the lithium is absorbed on the media, and then you have to desorb it using a huge amount of fresh water or acid. And the eluent oftentimes still contains significant concentration of calcium and magnesium, so you may have to do an additional step of calcium magnesium removal before you can get to a relatively clean lithium brine. So our goal is really to simplify this whole process. Right now the cost for this production is not very high, but the equipment cost is extremely high since you have to do multiple steps of divalent cation removal and absorption and desorption and clean and washing. So our goal is to replace this complex process with a very simple electrodialysis process, but with highly lithium selective membrane. The design of a lithium selective cation exchange membrane is challenging. You might have read the literature. There's a lot of effort trying to design lithium selective membranes, and it's relatively easy to develop a membrane that can select between lithium and calcium magnesium, but it's very challenging to design a membrane that can select between lithium and other monovalent cations. So what we did is we actually abandoned the traditional approach of making one layered cation exchange membrane. We use a design that's inspired by the structure of the reverse osmosis. So a thin film composite design, you may call it. In this design,
we use 3 different layers of materials, each provide a unique function. In the middle layer, we use a porous ultrafiltration membrane to provide the mechanical support. And on one side of that membrane, we provide a cation exchange polymer. So the ionomer there will allow separation between cations and anions. And on the other side, we have a skin layer similar to what you see in a reverse osmosis. It's based on polyamide, but in that ultra-thin polyamide layer, we also include a lithium ion sieve. So the lithium ion sieve has extremely high selectivity between lithium and other cations. So basically, it only allows lithium to transport through. But the challenge here is how do we embed this material in there but prevent other cations to transport through the polymeric matrix, because that's going to reduce your selectivity, right? So that's why we choose interfacial polymerization process to minimize the thickness of the polymer skin layer and to minimize the gap between these ion safe nanoparticles. So those are just some model simulation to show you that the lithium titanium oxide nanoparticles we synthesized in the lab is extremely selective to lithium. So sodium cannot pass through this material at all, and you can increase the transport flux of lithium through this material by increasing the electrical potential. And then in order to make a defect-free skin layer so that you maintain the high selectivity of the lithium titanium oxide nanoparticles, we first modify the LTO nanoparticle with amine functional groups, and we allow it to react with TMC, so one of the monomers you use to make the polyamide skin layer in the RO membrane. So this way we're hoping that this complex of LTO and TMC can behave like a TMC in the interfacial polymerization process. And we showed that yes, indeed, it did behave like a TMC. We formed a very nice ultra-thin nanocomposite skin layer, which has a very high density of the LTO nanoparticles in that polyamide nanocomposite skin layer, and was able to maintain fairly high selectivity between lithium and other competing ions. So here you can see final results. We are able to maintain very high lithium to calcium and lithium to magnesium selectivity, so about 150, and a decent lithium to sodium selectivity, so about 13, 14. Still not as high as LTO nanoparticle because we haven't optimized the polyamide matrix, but this shows the promise of such a interfacial polymerization approach, and also the thin film composite structure that allow us to independently tune the functions of each of the 3 layers, allow us to make a membrane that can allow precise mineral recovery from this complex wastewater. So, and this work was done by a large group of people, so I wanted to give them credit and thank them for their contribution in the past few years. Thank you.
Thank you. So one burning question. Anybody for this lithium and recovery from the oil and gas produced water? Anybody? Otherwise, we will discuss again. Thank you, Chilling. And we have last speaker, Professor Sang-Ho. He will talk about AI in brine resource recovery. So please join me welcoming his talk.
Hi everyone. As informed earlier, my presentation it will be about this AI with brine mining. And when Sean contacted me previously to talk about this topic, he told me that this is a very informal workshop with with small number of people. So I can just talk whatever I want to talk. So I prepared the presentation with this approach. And when I saw the presentations from 2 previous speakers, and I realized that he cheated me. Anyway, so the topic, the contents of my presentation will be really informative, and this is not technical. So I just want to talk about some concept and ideas, and I just also wanted to have some feedbacks from my presentation, because we have launched a project and we want to hear many ideas from many other peoples. Anyway, so my presentation will start with some background and motivations for AI for desalination and brine mining. And then I will also talk about the reason why we have to consider this. So why we need AI for brine mining. And then I will briefly introduce my project, which is called Promise. And many people will wonder why it is called Promise, and I will explain the origin of the name. And then these are really the preliminary cases, but I will just present the 3 case studies from a Promise project to show how we can combine AI with brine mining, and then I will also talk about the challenges. So desalination technology is evolving from the first generation technology of distillation to second generation of reverse osmosis, and many people have tried new technologies like MD, PRO, the FO with reverse osmosis. And I can call it as the 3rd generation technology. And now we are in the age of 4th generations. And many people will agree that 4th generation desalination technologies can have 2 directions. The first one is the distal desalination, and the second one is brine mining. And distal desalination is motivated by the needs of low energy consumption, and for not only the main desalination process, but also for the brine mining. And as for the brine mining, this comes from the needs for the environmental concern by brine, and also the needs for the circular economy, something like this. And so when we talk about the AI for desalination, there are many researches in the academia as well as in industrial sectors. And the reason why many people are considering AI in academia is to, for example, like to predict fouling and to perform some preventive maintenance, and also there are some needs for predicting the performances. And there are many reasons why we have to apply AI for desalination itself. And so AI models, many AI models have been applied for desalination. Some of the models are for the predictions, and some other things are for the classifications, and there are also some hybrid the algorithms. So ANN and GP and some other algorithms have been applied for desalination sectors. So as Professor Sean mentioned, there are a lot of papers regarding the AI for in these days. And also there are some clear trend of applying AI for desalination in industrial sectors. And there are several companies who are actually actively working on the application of AI. But in my opinion, these are rather preliminary. So they have just started this kind of approaches. So they have presented some concept, but they don't have a clear result yet. So we can say that we are still just in the early stage of applying AI for desalination in industrial sectors. Now we are talking about the reason why we need AI for brine mining, and we can just list some of the reasons why we have to consider, and those are all the demands for developing technologies. So these are the reason why we needed to develop new technologies for by combining AI with these brine minings. First of all, if you consider the brine mining problems, it's high-dimensional optimization problems because there are many conflicting outputs. For example, if you wanted to recover more resources, we needed to concentrate more, and we will spend more energy. And not just energy, there are all other factors affecting the whole overall performance. So in order to solve this kind of complicated problems, we needed to use AI for the process optimization, and this is one of the reasons why we consider this. The second one, brine mining requires the use of chemistry, and this is very complex because we are talking about more than 10 salts recovered from brines, and this non-linear chemistry requires the use of AI models rather than just some conventional, traditional models, and this is another reason. And AI actually can learn some plant-specific corrections, so we can just have more accurate predictions by using AI. And real-time control is also very important because many things will change with the time, especially in brine mining processes, because brine mining processes is a combination of brine concentration with mineral extraction, and the efficiency will change significantly when the environmental factors change. So that's why real-time control is required, and that also requires the use of AI. And another situation that we have to consider is the optimization needs for the product quality and the product cost, because when we recover minerals from brine, the actual cost change with the time due to the situation in the market. And at the same time, this process efficiency and other factors will change, and they will all make this problem very complicated. And again, we needed to use AI for solving this kind of problems. And in the future, definitely we needed to combine this brine mining with renewable energy sources, because in most cases, brine mining is energy intensive, and the use of renewable energy will actually create another complex situations, and again, AI will require for this kind of optimization. And the last thing is the lack of the experts in this field, because not many people can deal with the brine mining process, and in order to overcome this kind of situation, the system should be very easy, and that can actually help the operators to operate this kind of complicated processes. And these are the reasons why we start considering AI for brine mining. At this moment, I want to introduce the new research project supported by Korean government, which is called PROMISE, and this actually means the pioneering research on membrane-based desalination inducing sustainability and energy efficiency. So the name actually comes with this description of this project. Anyway, PROMISE means the promise, so we want to become a promise for the bright future of the desalination technology. In fact, this project has started this year, and this will last for the next 5 years. And this is a multi-million-dollar project. So more than $30 million will be investigated for this project for practical implementation of digital desalination and brine mining. So this project consists of 3 work packages. The first work package is about the digital desalination, and the second one is the brine mining, and the third one is the demonstration. So we don't want to just develop technology. Instead, we just wanted to just demonstrate the technology so that we can be ready for the market for commercialization of these new technologies. So the idea is very simple. So we will have desalination process, and we will develop new processes for brine mining. And the desalination process and brine mining process will be integrated and optimized by using digital technologies, including AI. And finally, we will build a pilot demonstration plant with a capacity of 1,000 cubic meters per day. And from that, we will be ready for commercialization. As for the first work package, and we focus on 3 things. The virtual design of the process, which means that we can reduce the time required for process optimization, and we can find the best condition for the process performance. And also, we will develop the AI-assisted operation technologies, so we can predict foulings and energy efficiencies, and so that we can support the people who actually works in this plant. And the final one is about the maintenance. So by detecting the fault of pump and ELD and some other devices, we can actually perform the predictive maintenance. So we have not developed anything yet, but after 3 or 4 years, we will have a prototype of the digital desalination platform. And we actually create an image for the future systems, just for your understanding. So this is not the real screenshot from the software. This will be the screenshot of the future products. But anyway, the reason why I'm showing you here is since we have 3 components in this digital desalination platform. The first one is about the virtual design, consisting of this digital twin synchronized with the real plants and the energy minimization modules, as well as the virtual design. So we can just change all the parameters in the digital twin so that we can find the condition for minimizing the energy consumption. The second one is the operation and the AI-assisted operations. So we will develop several AI models for fouling prediction, screening, optimization, and pre-treatment optimization. And then we will develop real-time decision support system so that people can also get some information from these AI models. And we also will develop the LLM-based interface. So large language model will be used so that the people can just communicate with the actual desalination systems through the interface, which is very similar to ChatGPT or some other generative AI systems. And as for the final, the maintenance, we'll develop some fault diagnosis and prediction modules, and also we will use AL and VL for remote maintenance of the systems. So those all these things will be developed for the next 5 years. And I just want to talk about some of the examples, and okay, I'll do that. First of all, let's just think about the reason why we need AI for brine mining. And AI has 4 steps. The first step is the things that, so when people wanted to do things faster, they need AI. So that's the first step, so that this AI model can do the things faster than the people can do. And the second step is that the stage that this AI can do the things easier than the people can actually do that. And the third step is that the advanced step. So in this case, the people can do better than actually people. The AI model can do better than the people can do. And the last step will be the stage of autonomous operation. In those cases, there is no need to have human operators, but this is the ultimate step, and we just wanted to stick to the previous 3 stages. As for the first case, so the examples of AI for pastel design. So we are developing the virtual the design interface and the systems. So this system is not only for the desalination system, but also the brine mining process. So basically the idea is there are some mathematical models as well as the AI-based models for the process design. And the conventional way of using this technique is that the people actually design for specific conditions, and they get the result, and they repeat until they can have some successful, some reasonable result. And instead of doing this, we just wanted to make an system that this optimization can be done automatically using the computer systems, so that we can reduce a significant amount of time when we consider millions of different combinations of operating these parameters. So we are actually doing currently for the reverse osmosis system to find the lowest energy consumption condition, and we are also working on these brine mining processes. The second case is for AI for easier operation, and as mentioned earlier, we are developing this interface based on large language model. In this case, we are aiming at the development of domain-specific large language model, and combined with RAG, real-time information feedbacks. So currently we have some prototype, but in the future we will actually have interface system actually better than ChatGPT. So you can imagine like we are developing a specified ChatGPT just for desalination and brine mining. So we are actually developing this technology, and with the limited time, I cannot explain everything, but you can just understand that we are just developing this kind of system one by one, and this system will appear probably within 2 or 3 years. The third one, we also try to use AI for a better maintenance. So in this case, we are just developing AI models for the brine mining process optimization. And in this example, we are focusing on the recovery of calcium and magnesium by mineralization, carbon mineralization. So again, this requires a lot of non-linear chemistry as well as complicated this optimization problems. So we are developing several AI models, and we have some complicated techniques to predict the performance. And with this information, we'll eventually develop these final systems. So since we have just started this project, so the result is not the final, and we are just going for these directions. So again, feel free to let me know if you have any ideas and suggestions for this kind of approaches. The last one, technical challenges. As you know that AI is not the solution for everything. Instead, it has a lot of limitations. So AI is a black box model, so we actually don't know what's actually going on inside this model. And model drift significantly, and its data is actually limited. So, and we wanted to have some abnormal data, but most plant data is the normal data. So there's a significant bias of the data for training AI models for desalination and brine mining. And there are some skill gaps that should be overcome. And the possible solutions that we can suggest is, first of all, we needed to go for the explainable AI rather than conventional black box AI. This will actually reduce the risk of the AI artifact, and we can use monitoring MLOP kind of approaches to reduce model drift, and we can create some generative data for overcoming this data bias. So there are several techniques suggested, and by doing this, we think that we can significantly overcome the challenges related to the AI applications, to desalination and brine mining. With that, thank you very much for your attention. Thank you.
So, any burning question before we start our panel discussion to Professor Sang-Hong Lee? No? So thank you for the distinguished three speakers. It's a very interesting talk about the real pilot scale of the resource recovery AI on lithium and then critical mineral from the oil and gas produced water. So now it's time to have a more specific question from the audience. If you have any other help or collaboration, so it's a good timing, we can discuss together. So, first, let me start from your presentation slide. I can start with the three of you. So, Chili mentioned about membrane distillation and then membrane crystallizer. It looks like you are utilizing the membrane distillation. No, it's different. So, forward osmosis. So this is more about osmotic assisted reverse osmosis, right?
No, it's actually basically forward osmosis where we apply a draw solution on one side of the membrane, and we apply the crystallization substance on the other. For example, as you've seen on the pictures, on one side of the membrane we have sodium chloride concentrated to about 250 to 280,000 TDS. On the other side, we're applying the magnesium chloride draw solution. Magnesium chloride is significantly higher osmotic pressure substance, and it takes out the water, and ultimately crystals start forming on the one side of the membrane. The membranes are tricellulose acid type membranes. They are not there is no thermal process involved of any kind. There is no heating. The only place where we are using basically cooling, not heating, is, as I mentioned, the draw solution. As it draws the water, it goes down in concentration. We start typically at around 380 to 400,000 TDS when the draw solution is applied. It goes down to about 280,000. And as we go through the cooling tower, we are actually, by just changing the temperature, we are reconcentrating it in a very elegant and efficient way. So there is no heat involved in any case.
All right. Because membrane distillation, so Professor Sang only mentioned about third generation of the MD and then some
Yeah.
hybrid system. So
Yeah, I mean,
promise project. So you are not continuing the membrane distillation based on your resource recovery, or are you still considering the membrane distillation for your brine resource recovery, like chilling's application?
No, currently we just wanted to focus on using ultra high pressure reverse osmosis and osmotically assisted reverse osmosis for non-thermal membrane-based brine concentration, because we believe that this is the way to reduce the energy consumption. Whatever membrane distillation we use, we always end up with higher energy consumption than these membrane brine concentrators. But since our project is also open to new innovations, so if we believe that some other technologies are actually better than our original plan, we'll very happy to consider the new options.
All right, thank you. So chilling, so membrane distillation you have experience. Do you have any like long-term application and how this can sustain for our brine concentrate more?
I really do think that if anyone can figure out a way to reduce energy consumption, would be great. And so far our multi-effect design was able to, by just the module itself, without any additional recirculation or heat exchanger, can get to a goal of over 5. So just simplify the membrane module design itself. But that's still very energy intensive because it's thermal. So for the oil and gas industry, their bigger goal is actually volume reduction. Generating clean water is actually a secondary objective for them. So if there is a way to utilize the ambient environment, because the ambient environment can actually facilitate the evaporation itself, if you can incorporate that the energy that you can draw from the ambient environment to further reduce the energy consumption for the MD process, I think that would be, any creative ideas would be greatly appreciated. Another thought in that aspect is the design, the similar technology, interfacial evaporation process. If you are not trying to harvest the clean water, interfacial evaporation in the state of Texas, because we have significant amount of land that's not being utilized, abundant sunlight, and that could be the most energy efficient approach. However, being a water person, I really wanted to figure out a way to harvest that clean water. If you use interfacial evaporation, the challenge is how do you collect the vapor and how do you condense the vapor using less energy?
Yeah. All right, so now it's time for open to audience. Do you have any question, and then come to the microphone? Then please.
Hi, good afternoon now. My name is Diego, coming from Aruba, Nikolai. I had a question on your presentation, because on brine valorization we focus a lot on different elements and things as well. But I noticed you mentioned the possibility for cement alternatives and what is going on with the coral restoration project or this type of projects. How do you see that fitting within the whole picture, and not just putting that in the ocean, but actual for construction materials and so on? How does that fit in the overall?
The use of brine minerals for cement production is beneficial in multiple ways. At this point, obviously, this is a corrosive substance, so as a result, if you do have rebar-based systems, those rebar-based systems have to be designed with special steel to prevent corrosion. So at this point, most of the structures we've done have been structures without any rebar in them. So those are architectural or coral reef-based systems. We're currently working on changing both the rebars and also the actual chemistry of the brine concrete to be able to start building rebar-based, supported structures that can carry very high loads. So that's the next step of our research. It is possible. It's a matter also of cost and applications. In NEOM, we do a huge amount of construction. About a quarter of the world's steel produced today is going into one of our projects. So as you can imagine, we do have a lot of cement and concrete involved. So it will be a valuable contribution to the industry. But it's not the main amount because the amounts used are fairly small compared to the amount of salts being produced. A 100,000 plant will produce about as much salt as a average size pyramid. So that's a lot of pyramids if you think about the number of plants we have.
Okay, please.
Hello everyone, I'm Omar from the University of Oxford, and my question for Mr. Nikolai regarding the concrete. Now, do you use it as slurry in its wet form, or did you think about using it as a powder? And also, did you think about accelerated carbonation or more like ambient curing?
Yeah, we're using it in a form of slurry. We're using 3D printing, so we're preparing a slurry and then a 3D printer that actually prints those shapes that I showed you on the pictures. So it is 3D based printing that we found is the most cost-effective way to go. We program it, and we have made all kinds of mainly architectural components using this to print also benches and other components that are functional, but without the ability to carry heavy weights. So chemistry-wise, we only have applied this in slurry. We have not created a powder application.
And finally, do you use like accelerated carbonation, or do you think there is a use for more ambient type of curing?
Yeah, we're not using accelerated carbonation. The process of making the concrete doesn't vary significantly from conventional making of concrete. So the process is fairly standard. It's the constituents that are included in the mineral constituents are what's really the valuable component of what we do. Our technology otherwise doesn't change the production process.
Okay, thank you. One last question for Professor Lee, and that's regarding your models. Do you see it as easier to integrate them with already existing, let's say, systems? Like how many billions of parameters that is needed for the software in this case, or your data system?
So let me get your question a little bit specific. So can you repeat a little bit more?
Yeah, like for your language models.
Okay, yes.
Yes, when you use them, how many parameters you are incorporating in the systems, like to make it viable?
Yeah, actually, we are working on this topic from like less than 6 months ago. So we are still working on determining the parameters required for this language model. But one thing that we are considering is that we wanted to make this model as small as possible, because people are currently talking about the energy consumption by this generative AI. So we just wanted to have a small but larger language model. But at the same time, we needed to make it domain specific. So with this concept, we will limit the number of these parameters. And we are going to start from some base model, and we will add some new knowledge and new variables and new information to these language models. So we are not starting from the scratch. Instead, we will make this model, and we will also reflect the outcomes from our project to make this model more domain specific.
Thank you very much.
So next, yeah. So in the meantime, Professor Lee, so when you have achieved your AI model after 5-year project, how much energy consumption you expecting to reduce from your AI control?
So you mean like
Energy
if
consumption, like you want to save the cost, right? Let's say energy or cost, how much you can reduce overall after 5 years?
so using AI model, basically we wanted to reduce at least 20 to 30% of energy consumption by design and the operation optimization. And in order to do that, we will need to use AI models, and this will also use some energy. But based on our preliminary calculation, although we needed to call these AI models frequently, we will have more gains of energy reduction rather than energy consumption by AI models. So we'll have net energy reduction using these AI models.
Hello, yeah, I'm Shantanu. I'm from University of Texas. I mean, either of the panelists can answer my question. I actually have two questions. Firstly, typical extraction of mineral from hypersaline brines involves, you have to reach concentrations close to the saturation level at least. So one issue with going that high in concentration is that you have a lot of scaling and other detrimental issues that can happen either in thermal or membrane-based desalination. So are either of your models incorporating that, or if so, if they are incorporating in the future, then what are the plans for that? So that's my first question. And the second question is, after you bring it up to the saturation limit, from what I understand, you have to send it redirected to a brine crystallizer where you actually crystallize the mineral out. So is the brine crystallizer also being modeled, or are the models as of now focusing only on the tertiary dewatering part? So, yeah.
So is this to my?
I mean, either of you.
It's a little bit.
Chile, give it to Chile.
Okay, so
Well, he was asking about modeling, but in the extraction process, so right now the industry standard is you obtain a clean brine first. You don't necessarily have to precipitate out the crystal. And then that brine is then refined to give you the crystal, and of course that involves sending it to crystallizer. But the brine extraction process, at least the way we're approaching, the traditional approach is exactly what you're saying. You add chemical, you precipitate out, and so you have a lot of scale formation in the system. And at the same time, you also lose your target mineral because it co-precipitate with other scale, chemical scale. That's why we choose to use electrodialysis, because this allows us to produce a clean brine, and you can concentrate that brine, but not necessarily to the saturation level.
Okay.
let me just answer about the models. And in fact, in our Promise project, our target is the 80% recovery. So this is actually part from these hypersaline conditions that we are talking about.
So this is 80% recovery for seawater or for brine?
Yes, seawater, the 80% from seawater. So it will be about 180,000 million per liter of brine concentration or more. But even with these kind of conditions, we also anticipate the scaling problems, and of course we will develop some nonlinear AI-based scale prediction models so that we can just make this operation stable.
Looking forward to that. Thank you.
Hello everyone, this is Jinghua from Clemson University. Jing like to know about more easy to remember. Currently we are working on desalination technology for agriculture purpose. So we were interested in nutrients. So the selective membrane are very interesting to us. So I'm curious about the selective membrane Dr. Lee could develop. Usually, like based on your understanding, developing a membrane, how to the real product, how long will it take to become a real product? And I'm also curious, like for current, like a critical project for the selective membrane, will it be possible to kind of directly cooperate with the academia professor? And like I want to know like how this selective membrane really used in the industry point of view, and from the develop to really use it, and how long it take as well from the first like industry point of view and from academia point of view, and also what's the main gap to let it become the commercial product.
Yes, selective membranes have, the concept of selective membranes was created about 3.5 years ago. So between then and the first prototypes, which are 2.5-inch elements of potassium chloride selective membranes, it took us about 2 years to create those. The key component to any of the selective membranes is active material that is used in ion exchange resins. If you think about ion exchange resin, there is an ion exchange support in a tiny substances called ionophores, which are complex molecules, organic molecules, which are designed to allow only a particular substance to go through, and then the others are rejected. The way we were able to achieve the rejections, we were able to achieve about 85 to 95% rejection in letting a particular mineral to pass. And that was possible by having multiple layers of ionophores, one above the other, because if we just have one layer on a conventional membrane, we achieve about 30 to 40% passage. We are using 7 layers to achieve 85 to 90% passage. And those are macro layers that are put on the membrane one after the other. Once we get to that point, we're currently actually testing 2.5-inch elements with potassium selective membranes to verify over a long period of time their ability to sustain selectivity. The principle of what we're using can be applied to technically almost any mineral. As long as we can extract it by ion exchange, that means that the ionophores already exist. The ionophores that we are using for our membranes is actually a commercial product, which is not patented. So anyone can use it to make the selective membranes themselves. The one huge benefit of selective membranes is they dramatically reduce the transmembrane pressure. So for example, one of the answers of how do you get from 2.27, which was the SWCC record of energy, to below 2, is if we use selective membranes, the transmembrane pressure goes from about 20 to 24 bars down to 12 bars. 12 bars is over 20% reduction of energy, so 2.27 becomes less than 2. That type of possibility exists for any of those because the benefit of that energy reduction comes from creating technically molecular paths for the water and the mineral to go. The way the system works is both water and the particular mineral we're selecting goes through the membrane, so it goes on the permeate side, on the clean side of the membrane. Now we have a mix of clear water and the mineral. The water then goes, this mix goes through the second stage of the system. That's usually brackish water arrow membrane. And that brackish water arrow membrane is conventional membrane. So as any other conventional membrane will do, it will separate the salt from the water. So we end up still producing drinking water, and all the particular mineral, like in our case potassium chloride, as I gave an example, stays in the brine. And there are two stages in a conventional brackish water, second stage brackish water facility. So we end up with concentrating it and recovering about 85% of the total amount of mineral that was initially in seawater directly without increasing the energy, actually surprisingly by decreasing the total energy of production of water and producing that mineral at the same time. The cost of production of the membrane, we're currently commercializing the product. We're working closely to create commercial products, I should say. We're commercializing the product with DuPont. So DuPont is using and testing the system, and we're working on 4 membrane elements: lithium, potassium, magnesium, and rubidium. Those will be selective membranes for production of those 4 substances. Commercialization itself, based on our discussions with DuPont, will take about 2.5 to 3 years before those membranes are actually available as commercial products guaranteed by DuPont on the market.
Thank you.
How about Celine, from the academic perspective?
I guess I'll share our experience and lessons learned also. I guess that's the reason why we choose the thin film composite structure, is because you wanna, when you start thinking about designing a membrane, you wanted to make sure that it's manufacturable, right? If you come up with a protocol that's very difficult to scale up and the industry currently doesn't have a way to make it, and it's going to be, the process of commercialization is going to be very, very long. But the lesson learned is that, okay, even though the thin film composite structure in theory is very similar to the reverse osmosis, what we didn't realize is how critical the substrate layer is. We thought, you have a microporous layer, provide mechanical structure, how difficult is that? Currently, every auto membrane manufacturer has their own substrate. Unless they form a partnership with you, they'll not tell you what the exact substrate they use. And in our case, we are not using the non-woven. We just have the polysulfone or polyether sulfone layer, and that causes a major challenge in their fabrication, because their current production process requires that strong mechanical strength provided by the non-woven. It was adequate for us to make it in the lab without the non-woven, but when you go to the road-to-road production, that becomes a problem. So I guess my lessons learned is you have to start talking to the manufacturers early on.
Thank you. Appreciate for your detailed answer.
Thank you. Please, next.
Yes. Hello. My name is Felipe Torres. I come from Australian National University. And my research group developed an all-liquid thermal brine concentration method called multi-channel thermal diffusion. And we're excited about this technology because it's membraneless and no evaporation, and it's targeting what we think is the Achilles heel of brine valorization, which is brine concentration when you feed is above 200,000 ppm. So my question is, I have 2 questions actually, one from Nikolai concerning his membrane crystallizer. I saw that you had improved feeds between 300 and 350 ppt. What was the lowest concentration you've tried for those feeds? Have you tried anything like 200 ppt or so, and what's the energy consumption for that?
Yes, the higher the concentration, the faster the process. So there is a direct relationship between the concentration of the brine that we feed and the actually flux of the membrane. So if we operate at 250 to 280, the flux doubles compared to 200,000. We have done 200,000 as well because salinity could vary for various applications. Just to give you a sense of how quickly we're creating the first crystals and beginning crystallization process. If we had 280,000 TDS, it takes about 15 to 20 minutes. We start creating crystals and we're in continuous production of crystals. If we had 200,000, it takes about 4 hours. So the flux that we have to apply drops in half. That means that the system becomes much bigger in size. That's why we're striving to maximize the concentration of the feed. And it becomes more important than thermal systems, because in thermal systems, every thermal crystallizer has a pre-evaporation component. So even if we put it at 200 to 250 or 280, the pre-evaporation component always will bring it to 320, and then put it into the crystallization process and then crystallize it. In membrane crystallizers, we don't have any pre-concentration. It just goes through the membrane and affects the flux.
I see. Have you, in a follow-up question, have you done like scaling, fouling, long-term testing for those membrane crystallizers?
Yeah, we've been running the crystallizers for about, there's only one crystallizer, I should say, not crystallizers, but we tested different membranes in different substances, but using the same exact membrane that you've seen on the picture. We've been testing for at least 6 months, I would say, on sodium chloride, because that's our main product. And on the other products that I mentioned, calcium carbonate, for example, we've been testing shorter. Potassium chloride, we've tested also about 2 months. The overall process is very reliable, and the loss of magnesium chloride that we get through a little bit of evaporation and through the column is fairly easily compensated by the magnesium selective membrane, which provides us with new magnesium chloride directly extracted from seawater. So basically that allows us to get to the point of zero chemical being purchased out of the system. The magnesium chloride is produced directly from seawater by selective membrane for magnesium chloride.
Okay, so thank you. And just a question for Qilin Li, Professor Qilin Li. I had a question concerning your membrane distillizers. In one of your figures, you had like they go up to concentrations of 200,000 ppm. Have you tested for higher concentrations, and how do they behave?
250,000 is the highest we've tested, and that's our feed concentration. So we haven't, for sodium chloride, we haven't tested all the way up to crystallization, but for other minerals, yes. As I said, these HBN coating is extremely resistant to attachment by mineral crystals. So we do see accumulation of crystals on the membrane surface, but not on the HBN surface, so you can actually wash off pretty easily. But again, those are all laboratory scale testing and relatively short term, so we don't know if you, the longest we've tested is only a few weeks. We don't know, if you run it all year around, whether they will eventually start to accumulate on the surface.
Nice. Thank you very much.
Thank you. So, we have.
I thought it would be nice to switch sides for a moment. I'm Marc Philibert. I'm with Suez. I have a couple questions in terms of sort of practicalities for market, right? First of all, you mentioned like there's potentially more in the oceans than terrestrial mine, but for that to become a reality, then you have to make sure that you're producing it at a lower cost than the terrestrial brands. You mentioned that you mentioned that that's the case, but we don't have any numbers. Is that the case for all the minerals? Do you have numbers that show that brine mining from the ocean is cheaper than mining from terrestrial mines?
There was a graph with, there was a graph with dots. There was a dashed line and black dots and white dots. The black dots are all minerals that we today, with the technologies we know and have, cannot be competitive. The white dots that are above the dashed line graph are all minerals that we actually can produce with the current existing methods of production. We can produce it more competitively than terrestrial mining. So that graph basically shows we have about a third of the minerals that are of value, our technologies exist for them. The rest, you guys here have to figure it out. So you're the scientists. But the reality is there is a great opportunity to make those other minerals possible to harvest as well. It becomes a matter of how much is it, just to give you a sense. 100,000 cubic meters a day plant contains gold. But the total amount of gold, if you extract it with 90% recovery, because technically nothing can be extracted at 100% recovery, that will be about 5 kilos. You know, it's certainly not worthwhile. Not at today's markets of gold. Maybe, you know, if gold goes 10 times higher in price, they will at one point or another. So there are really two important issues: the price of the mineral on the markets and the cost of production. So as you noticed on the graph, and I can share it with you if you're interested, there is still a lot of work to be done for many of the minerals.
I mean, I've seen that graph before, but the way I interpreted it was, okay, we're able to, our cost, mining it from the ocean is less expensive than how much you get from the revenue. However, that didn't necessarily mean to me that it was cheaper to do it from ocean brine mining than from actual terrestrial brines, because they might be still even more efficient and cheaper. But that's fine.
Yeah, this is based on the numbers that you see on that graph, are based on commercial values of the minerals that are available on the market. When we create the value, this graph, we look at how much we can produce the mineral for, and what is the value for that mineral on the market. And the market value is established by terrestrial mining, as you know. It's not established by seawater. Seawater brine mining is in its beginning. So the information we have on the terrestrial markets are the market values that we see today.
That's fair.
So that's how we compare, and that's how this graph was established.
Okay. I have a follow-up question to that. The other issue with market, and I think Dr. Lee sort of mentioned that at some point, is that, for example, NaCl, we know if we were to produce the NaCl that we have in one of the huge plants, we produce more NaCl than is sold globally. So you're gonna overflow the market with something you cannot sell. The same thing could have been said with the lithium for your brines, where you said you have 3 times the amount that's being sold in the US. So my question is, what are really the minerals that we can find? What's the level? Because brine mining, ocean desal, if one plant is able to produce enough NaCl for the world, it's not going to be very interesting for everyone.
Yeah.
So do you have any conclusions as to which are the minerals and where, you know, the limits are?
Yeah, I mean, there's always limits to everything, as you pointed out. If all those desalination plants have a brine mining facility that makes salt, we'll flood the markets, the world markets with salt. And in that case, we can compete with terrestrial markets only if our cost is significantly lower. And that's why I gave you an example of solar salt, because most of the markets for salt today are based on solar evaporation ponds that make them. Those ponds, the cost, the sales price of those from terrestrial sources, obviously, is about $25 a ton. That's what you would buy it from. And it's only at 96% purity. The cost of production, considering membrane crystallization that we have today, is $18 a ton. So realistically, we can compete even with lower quality markets, but $18 a ton from 99.6% purity. As far as the demand for it, as we know, the world is moving away from oil, and therefore there will be surplus of oil in the Middle East, which, with the salt available, would, you know, result in higher productivity of plastics. And you would say plastics are really not a good thing, because they may impact the environment, as we've seen it impacting the oceans and others. That's why the Saudi government is investing in a huge program, which you've never heard of, jointly with the US, is to create plastics that are made, as I explained, from these two materials, but plastics that are regenerative. What that means is you have a piece of plastic, you grind it in chips, and you use these chips to print other component or the same component. Currently, the technology we have available today is you could reprint that piece, turn it into chips, and reprint it 10 times. With regenerative plastics, the demand for plastics will increase dramatically, because we can actually replace almost everything. So the Saudis look at the future as the moving from Iron Age into Plastic Age. And plastic cage will require a tremendous amount of oil and salt. So that's how they see oil and salt moving in the future. So they are investing in these technologies because of the longer view of where they'd like to be.
Okay, thank you very much.
Just one thing that I want to briefly mention here about the economic feasibility, and as far as I know, economic feasibility depends on whether the actual consumer exists or not. And so if the demands exist, it will have economic feasibility, and demands actually depends on the quantity and the purity. And in our Promise project, we aims at economic resource recovery, which means that we are first looking for the consumers, possible potential consumers, who are willing to purchase a certain amount of brine, salts or products from the brine, and we just specify. We just know about the specification and purity and actual amount of these needs for the amounts, and based on that we can develop the technology, and this will make this brine mining more economically feasible. And at the same time, we are also developing some technologies which are not currently economically feasible. But the reason why we are doing is, as you already mentioned, we don't know about the future price changes. So sometimes some minerals, which is economically feasible right now, but in the future they may not be. And there are also some minerals which are not currently economically feasible, but we don't know about the future. So we just want to be ready to have technologies for the future changes, and this is the approach that we are actually taking.
Thank you.
Thank you. So we have a lot of experts in this room. So I just want to pick up two people and have a brief perspective of brine resource recovery and AI. So first person is Professor Miriam Balaban, and second person will be Professor S.K. Hall. So let him escape start first, and then I will go to you, Professor Miriam Balaban. Just overall your perspective of brine resource recovery and AI. How do you feel like based on your experience? Please, S.K. Hall, can you come and share your perspective of brine resource recovery AI? 2 minutes.
2 minutes. Hello everyone, I'm S.K. Hong. I'm a professor at Korea University. I didn't expect he's going to ask that question. But I have a keynote speech on Wednesday regarding industrial wastewater or achieving circular economy in industrial water treatment. I think the technology that we are developing for brine management in seawater desalination could be a key technology for achieving circular economy in industrial water treatment. And recently I'm working with Samsung electronics as well as battery industry in Korea. I mean, in Korea now the high-tech industry requires lots of water, as well as they try to recover some of the valuable materials from their industrial process. For example, battery industry, they try to recover lithium and cobalt, nickel, and all those metals. And also semiconductor industry, they try to recover some of the acid that they are using them. And so by hearing all this new technology development in seawater desalination, and also I involved in those development as well, I think we can apply this one to other high-tech industry, and then in that case, we're talking about feasibility of economics of recovering all those valuable materials. Maybe those industry, high-tech industry, economic feasibility is much better for our technology. That's my comments. 2 minutes, right? Okay, see you at on Wednesday in my talk. I'm going to talk about technology over there.
Thank you, Professor Hong. So his talk will cover continuation of the resource recovery. Now is time for our mother of desalination. So she will share her perspective on brine resource recovery and AI. So I cannot. This one is right.
Okay. That's all right. In my years of editing desalination and desalination and water treatment, brine was considered a waste. And then suddenly, not many years ago, very recently, it became of value. And first of all, then we have these sessions, this work that's going on. Suddenly, it's not too long ago, it's just a few years ago. And also, so brine became of value. And then also the European Union assigned a project, C for Value, of which I was a participant. And we also studied all these wonderful possibilities of using brine and of the value of brine. So this is really what I have seen, and we continue to get more and more papers and see all the people who are now involved.
Thank you, Professor Miriam Balaban. So, anybody, I'd like to share about your strong perspective of brine resource recovery or AI. Just 1 minute. Nordi.
1 minute.
Making a lot of people in trouble. Okay, let's go AI.
AI, that's fine.
My friend.
Yes.
So I was very actually surprised that you mentioned that AI is future generation of desalination. AI is the future, yes, but what's the link with desalination? I mean, we will modernize desalination, we will make a lot of optimization. But I was expecting the next generation is about technology, not, I mean, desalination technology, how to go into a new membrane or new other process. So why did you call AI as a new generation instead of saying like it's a tool actually we will get a lot of good things. Optimization is one, prediction, early prediction, fouling, etc. But why you call it next generation of desalination?
I expected some kind of perspective, but he actually asked a question, so what a surprise. Yeah. Yes, that's a very good question. Actually, as briefly mentioned in my presentation, desalination process is becoming more and more complex. So previously, it's something that's a little bit formal, but now we are facing new challenges and new problems. And of course, this brine mining will add more complicated problems and situations. And of course, we can do without AI, and AI is a tool, but we can do better with AI. This is, if we have very good tools, why don't we just use these tools? And as mentioned earlier, we can save a lot of time, we can improve the efficiency, and we can make it easier. So this is why AI is inevitable, probably in the future for the desalination. And another thing that we have to consider is we have developed new pumps, new ELDs, new membranes, and new processes, but it's coming to some kind of limitations. How can we further improve the hardwares? When we improve the hardwares, at the same time, we also have to improve the softwares. And AI is one of those kind of softwares that can utilize the full performance of the current hardwares, but we can actually have better performances without spending smaller amount of money. And that's my perspective on using AI for desalination.
I can still give a perspective. So, 30 seconds for perspective. I remember Professor Dior, first time he was in our committee, long time, like 5-6 years ago, when he said desalinated water will become byproduct. I mean, and this is what we heard today from Witchcom. The second thing is that we all thought that sodium chloride is actually not that good value or high value, and we have huge amounts of sodium chloride and we cannot even sell it. Today I hear that sodium chloride with the oil we can replace a lot of things, and actually which is one of the directions for resource recovery. Because if we go back to lithium, we work with lithium, including imported water from Saudi Arabia. We all know that the concentration of lithium in seawater and in brine is very low, 0.2 ppm, 0.4 ppm. It's very hard to make it economically feasible. The best thing we can get from imported water is 200 ppm, maybe 500 ppm. Imported water, which is a very challenging feed water stream with a lot of other challenging stuff. So it's difficult to make it also economically feasible. So now the main challenge for the resource recovery from brines is actually how to make it economically feasible. Sodium chloride is one of the good news because we have plenty and it's much easier to get, and if we have a market, because at the beginning we in Saudi Arabia said who will take this sodium chloride? Nobody will. There is no taker. It's very cheap and huge volumes, but actually there are some applications.
There's strategy behind.
So that's strategy behind. So let's push forward on this topic. Don't be discouraged because the economical feasibility is very tough compared to other conventional processes.
So what's the strategy for the existing market of sodium chloride and then brine sodium chloride? Can you share your strategy from Saudi Arabia, even Qatar?
Yeah, as I mentioned, the strategy is to increase dramatically the use of sodium chloride because of the production of plastics. And that is only possible if we actually have plastics that are possible to regenerate and recycle multiple times. Once that is possible, that will dramatically increase the demand for it. That's one side. The other side is the quality of the plastic products. It's not a huge secret to say that the latest models of US fighters are actually plastic. They're composite plastics. They're not steel, as you may think they would be. And currently we're using technology that I explained to deal with logistics. As you can imagine, if I have a spare part I have to ship from the US halfway around the world, that will take me usually at least 6 to 8 hours, even with the fastest planes. Well, now you have a way of printing that component on site in a matter of hour or less than that. That is going to regenerative ability of plastics to be regenerated and reused this way, locally, in your site, beats many of the logistics challenges that we've seen. It basically defies borders. You need a spare part for a pump. You don't have to wait for 6 months as we do in Saudi often. You just get the software, you print it at your home. Or you can have a scanner that can actually make a scanned copy of what you wanted to do and print it. And that's in a matter of hours, not a matter of 6 months. That will change dramatically environment as well. We no longer are shipping, we no longer are flying planes, spending fuel on that direction. So that's why I do believe that the strategic approach of producing regenerative plastics at low cost would change the world, the demand for plastics and therefore demand for salt. So I think that's what both US and Saudi Arabia do believe will happen.
Thank you for sharing.
I just want to briefly mention one thing about this economic feasibility of brine mining. And one way that we are looking at is the carbon capture, because since climate change is becoming worse and worse, and the carbon credit will become more expensive, and since brine mineral carbonization is the carbon mineralization is one of the very good methods for carbon capture. So if we can just look for the, going for this way, we'll have another benefit, the revenue created from brine mining.
All right, thank you very much for the very valuable discussion together. So we don't have time, so you can you have to do after this session. Please, you can have a personal discussion together. We have to go next step. So next step is so what we need go for next step. So industry perspective, academic perspective, also some of the oil and produced water. So what's the major? Okay, one. The most challenging problem you have, and then what you can do next step. Potentially we have a collaboration, so potentially you need some other specific technology development or policy development. So please, only one most challenging barrier, and then what you can do next step. Can you please share?
Yeah, the next barrier to break is basically creating integrated desalination and brine mining systems, which are designed around the brine mining component. First, in order to do that, to me the main component or the main field of research will be multifunctional membranes. For the last 50 years, membranes have been doing only one thing. Think about nature. Our cells, or anybody's living creature's cells, do not do only one thing. They are multifunctional. So for us to be able to optimize that benefit between producing water and salt, we do have to use multifunctional membranes. And as I mentioned, in our case, the solution that we did see is the selective membranes that allow us also to, if a mineral expires, it's no longer interesting for the industry to replace those membranes into the same reverse osmosis system with others that are focused on something else. Flexibility and multifunctionality, those are very key.
Thank you. Flexibility and the multifunctionality of membranes. Yeah. Yes, that's great.
I will talk about in terms of this brine mining and AI with brine mining. In the academic the point of view, many people have actually studied brine mining and brine resource recovery, and many new materials and new techniques have developed, but it's very questionable how many technologies can be actually accepted by industry. So it's very good to carry out some works for submitting the papers in high-level journals, but at the same time, it's also very important to make this actually happen in real-life situations. So in the academic sectors, we needed to actually develop the technologies that may be also useful in industrial sectors. So there should be a link between this academia and industry, and this is one thing that we needed to do for the brine mining in academic sectors. And as for the AI with the brine mining, in fact, there's a limited available data that makes really difficult to apply AI for brine minings. So there should be some platform to share the data and share the result, so that we can facilitate this kind of research works. And we hope that Promise project can be one of them, but we can create another platforms and conferences and workshops to make sure that we can have enough data and enough models, and they can be shared and they can be used to have some meaningful results for brine mining. That's all.
Thank you.
I was going to say multifunctional membranes, but since Nikolai already said that, I'm going to say something different. I think we really need to accelerate commercialization of innovation that come out of academic labs. There's so much knowledge in this room on desalination and brine management. But if you look at the industrial wastewater side, for example, I'll go back to produced water. this industry is actually willing to pay a lot more on desalinating their wastewater. Right now, their benchmark is $10 to $15 per cubic meter of that wastewater desalinated, which is, to us, would be, for those of you who work on seawater desalination, that's a very, very high price tag. But their challenge is, even though they're willing to pay more, there are no commercially available, mature, and proven technologies out there. And they're a very conservative industry. So what I'm trying to say is we wanted to see more of the industry partners jump in, be the early adopters, and help de-risking new technologies faster. There's so many bright, brilliant ideas coming out of the research lab, and not all of them will become commercially viable technology, but we need people to help us de-risk them and figure out which ones will never work, which ones will have the potential, so that we can accelerate that commercialization process.
Thank you for the wonderful comment. Just to summarize the key point for the three main speakers. So we need to have more flexible and multifunctional membrane for integrate the desalination, which will lead to our desalination translation opportunities, as well as some of the new AI-related data collection, which will give a more future collaboration. And finally, we need to have a more resilient adaptiveness of this commercialization opportunity between industry and academia. So how we can work together to make this opportunity, research and industry to have a good collaboration. So that's the key message we have from our distinguished speakers. And thank you for your attention. And then we'd like to continue this Brine workshop for the next Desal 2027. This is a biannual conference which will be held in Shanghai next 2027. So please continue to work together. And before that, we want to have a special issue for this Desal 2025. So you can submit any kind of topic, also Brine, AI, membrane, any of the translation opportunity. So if you have any good idea today from this Brine workshop, so you can make 2 pages of communication, maybe long in your paper, even very specific perspective paper, research paper. So please, you can submit. It's already open for the tab of the desalination submission journal. So next step, you need to write, continue to engage. So looking forward to seeing you for the next Desal 2027. We will continue for this workshop. And then let's thanking to our 3 distinguished professors for the so we have time. So we have,
I just wanted to add one thing. On the last day, the 19th, we do have a brine mining session in the morning. So if you're interested to hear more about brine mining, more specific technologies and details, check your schedules, 19th in the morning, brine mining session.
Absolutely, you can have a more specific. Thank you for your attention, and looking forward to continuing discussing during this conference. Thank you very much.
Was it helpful? Your early career? What did you learn?
I gave the poster connection.
Oh yeah? Okay.
That session, mostly I learned how to network with other researchers.
Especially professors. Other PhD students is easy to network.
Oh, really?
To network with other professors, not so easy. Do you want to say hi to Chilling? Let's go. I want to say hi to her as well. Oh, she's very nice. She will not be ready.
How are you doing?
because you know that how it was,
Business One of the will make a good
아, 봤어. 예. 제가 답변 안 줬죠?
아, 예.
어?